Thank you for telling me that. Good afternoon. Okay, so even though many people have not come yet, I will start on time. And it is a pleasure to come back. You will remember me from the first week of this course. And there, what we did was we looked at a general introduction to astronomy, astrophysics. There were a lot of questions. Very happy with the number and quality of questions. And later on, I hope a lot of these questions were also answered by some of the other courses that have taken place now. I will spend two more lectures today and tomorrow in the afternoon talking about groups and clusters of galaxies. You already know what galaxies are, but collectively they are very interesting. That's kind of my area of research work for most of my life, to look at aggregates of galaxies. Okay. So I'm going to start. If you remember, when I gave the general introduction, I talked about how galaxies form the basic building blocks of the universe, kind of molecules of matter, galaxies of the universe, and the fact that we didn't actually notice, the fact that we didn't realize that it's the galaxies that are the units of the universe till less than 100 years ago. And this is why it's a very new subject. The interesting thing, of course, is that galaxies are, if they live in various aggregates, they don't like to live on their own. You can find very few galaxies that are completely isolated. And because they live in aggregates, groups, clusters, superclusters that I'll talk about in these two lectures, you will see that there is all the hierarchy of structure in an interaction. And galaxies, since they live in small groups, often they interact with each other. As you can see, there are pictures here of galaxies colliding and merging, and in various ways interacting with each other. And I talked a little bit about that in the introductory lectures. And we also said how the average distance between galaxies is megaparsec. Of course, when a galaxy is in a group, this doesn't hold because the galaxies are closer to each other compared to the average distance between them. I talked about how our galaxy, the Milky Way, this of course is not a photograph. You can think about us being in a part of a galaxy that's not in the center, but looking out on the universe from this kind of vantage point, which is now nowhere near the center. And the fact that we are part of a small group, and I talked about some of the other members of this group, and this is the beginning also to think about now galaxies being in larger systems, which means that the local neighborhood is called the local group. And in this particular group, it's a small group. Two galaxies, two major galaxies, one the Milky Way and one Andromeda. They're falling towards each other, as I showed you in that simulation that I showed in the very first couple of lectures. And they have lots of satellites around them. And this is the Andromeda galaxy, which is that one, which as you see, and this is a real photograph. And you can see that this already, you can see two satellites, NGC 205 and 32. And then if you look very closely, not in this photograph, but in the photographs, you will see other of these satellites that you see. Now, examples of nearby galaxy groups are like this. And this also shows the scale of interaction. You can see these are nearby galaxies. This is very nearby, about 5 megaparsecs away. Like that, our galaxy, our local group is about a megaparsec in size. A few megaparsecs away, you have this system of M51, which is a very nice grand design spiral with a a much smaller galaxy M52, and it's a very deep photograph. And you can actually see what the effect of this interaction is doing to this galaxy. There are lots of stars, stellar streams being strewn around, and this interaction is then and I'll call this a group because there are two galaxies, but there are also small galaxies all over that you don't see. So this is an example of a small group like our local group, except that in this case there's one big and one small. In this case, a very famous Stephan's quintet. This is a very interesting picture because this is a combination of an optical picture from the Hubble Space Telescope and an X-ray image of the same group. And the blue bit that you see in the middle is from the Chandra X-ray Observatory, and it's only the X-ray part. So actually, you can see 5 galaxies in there. 1, 2, 3, 4, 5. It turns out, after doing a lot of research, we found that this galaxy in the foreground is actually in the foreground. This galaxy is not part of this system, which is very colorful, is actually right in front, in the foreground. And actually with the Hubble Space Telescope, we could resolve this galaxy into individual stars because it's so nearby. Otherwise, it's about, this system is about 70 megaparsecs away. And these 4 galaxies form a quintet because we thought it was a quintet. But the interesting thing is there is this system of very hot gas emitting X-rays, which you don't see in the optical image because it is 10 million degrees hot. And that is because the galaxies are ramming together, and the gas in between, because of the motion of the galaxies, the thermal motion, is heated to very high temperatures, as high as 10 to the power 7 degrees, and it emits an X-rays. A good example of how you can use different parts of the electromagnetic spectrum to find out what's happening in taking images all along the electromagnetic spectrum. I'll give you more examples of how X-rays and radio waves and optical light and UV and putting them all together tells you much more than what you see in simple optical images of galaxies. So these are examples of groups, and most galaxies live in groups like that. In this case, a group of 4. In this case, a group of 2. I'm not counting the dwarf galaxies. In our local group, it's a group of 2. Whereas at the other end of the mass spectrum, as it were, you have clusters of galaxies. These are the very, very rich clusters. And how many galaxies can you see in this picture? This cluster has many hundreds of galaxies that are as big as our galaxy. So on one end, you have the local group, 2 galaxies. You have M51 with 1 big galaxy and 1 small galaxy and lots of dwarfs. Not using the dwarfs. In this case, you have 4. And in this case, you have close to 500 of them. And that's a very rich cluster. And there are many such rich clusters called, these ones are called Abel clusters, which are rich clusters. And anything that has more than 30 galaxies, 30 galaxies, size of our galaxy is called a cluster. Right? And again, we're not counting the dwarf galaxies. So this is an extreme example, but one of the most well-known clusters, and there are some very interesting gravitational lens features in it, which I'll point out later on. So in this simulation that I showed you before, this is a simulation of dark matter, simulation of the distribution of matter on a very large scale in the universe. And you can see we're talking of that being 100 megaparsec. And so this whole thing is many hundreds of megaparsecs across. And if you're looking at the distribution of matter all over, then individual galaxies would be little things like this, those little yellow blobs. And a group would be maybe 1 or 2 big galaxies and some small galaxies like that. Okay. And a cluster would be somewhere here, where you can see already, you can probably take a much larger chunk like that, and you can see that's where all these filaments of matter cross. And you would see you can count easily lots of galaxies in there, and that would be a cluster, right? So here is another example of a cluster here. And structures like these would be groups, small groups, 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 etc. So there are more groups, many, many more groups than clusters. In fact, this is a very complicated plot, and I would like to spend some time explaining a plot like this, which kind of shows that most galaxies are in small groups than in clusters. So here's an example. Just look at the left-hand side plot, not the right-hand side. The left-hand side plot, the x-axis is in units of log 10 to the power. The luminosity or the total light in a system, by system I mean um, an aggregate, in which a system taken from a real survey, a three-dimensional survey of galaxies, in this case the 2DF survey, but there are things like the Sloan survey and various surveys, in units of luminosity of the sun. So this, for example, is 10 to the power 11 times the luminosity of the sun. Okay. See, in our galaxy, for example, our galaxy's mass or luminosity, our galaxy's luminosity is 2 times 10 to the power 10 times the luminosity of the sun in these units. So our galaxy will be somewhere, the Milky Way would be somewhere here. Okay. Our local group is essentially twice that, because there are 2 big galaxies and some tiny galaxies, so maybe 5 times 10 to the power 10. So that local group would be here, somewhere here. I hope you can see my arrow. It's right in the middle here. Now, what does the y-axis say? The y-axis says it is the number, it's just a histogram, in fact, the number of systems, of galaxy systems, that have light, the value of which, if you add up all the galaxies in there, and total amount of light from that system is on the x-axis. So that's just the number. This just tells you that this histogram of the total light or luminosity of systems peaks at about the size of our local group. And if you look at the very, very rich clusters like 1689 that I showed you, Abel 1689, which has a few hundred galaxies in there, their total light is of the order of 10 to the power 13, 100 times more than the light that is in our galaxy. And that is right out here, which means less than 1% of galaxies lie in clusters like that. So this is a very revolutionary view. I mean, when I show this plot, a lot of people don't believe this, because a lot of people like to study lovely, nice, rich clusters, which have, as you can see, hundreds of galaxies in them. When you take a single picture, you see lovely galaxies, etc. But they are very, very rare compared to where the main galaxies are. So on the cosmic web, that picture that you saw, galaxies are born in small little villages, small little groups. And slowly these groups merge to form larger and larger groups. They move along those roads and they end up in the big cities, as it were, the big clusters. Towards the end, after much of their life has happened. So if we want to understand how galaxies form, how galaxies evolve, how galaxies spend, where they spend most of their time in their lifetime doing what, then one has to study not just clusters, but away from the clusters, the small systems. And this is why this is a new field of studying of galaxies in small groups, studying galaxies, how they evolve in small groups. And it is found that in clusters, galaxies are in a state where they've essentially ended their evolution. Not much star formation happens in galaxies in general, in clusters, whereas in groups you can see a lot of interaction happening. Okay. So these are different scales of galaxies. So let's start by looking at, and I hope a lot more people have done now. Let's start by looking at what are these clusters and groups of galaxies? What are they made of? So of course they're made of galaxies. That's obvious. You take a picture, you see lots of galaxies. That's how you identify them. But and galaxies are, as you know, the visible part of them are made of baryons, and they are made up of quarks, protons, and neutrons, and those are the things that make the stars. And the stars are give you the luminous parts of the galaxy. I also said that galaxies themselves have dark matter around them. This was the whole point of the last lecture of my introductory set of talks, where we said that we can find from the spiral galaxy rotation curves that there is dark matter halos around the galaxy. Right. But clusters themselves, in addition to the dark matter around the galaxies, have dark matter on their own. In fact, the cluster itself is full of dark matter holding together the galaxies. And I'll show you the evidence for that in a minute. So what are they made of? They're made up of galaxies, and they're made of dark matter that holds together galaxies. So it's not just the dark matter around individual galaxies themselves, but the dark matter that holds together all galaxies. And then within this system, so that itself creates, because this is a gravitating system, a gravitational potential well. In this gravitational potential well, you have all kinds of gas, which is in the form of plasma. There's hot gas, which, as I showed you some example, 10 to the power 7, 10 to the power 6 degrees hot, which emits X-rays. I'm sure there is gas that's 10 to the power 4, 10 to the power 5 degrees hot, but we can't detect them directly. Very difficult to detect them because they emit things that are absorbed on the way, and also our instrumentation is not very good at detecting far UV. Then there is colder gas, which emits in the radio, and then there is molecular gas, which emits in the radio and millimeter waves, things like this. All kinds of gas, hot and cold gas. But this is also baryonic. And there are stars in between the galaxies that result from the interactions between the galaxies, and stars are pulled off galaxies, and then they haven't ended up in another galaxy, and the stars are moving around. So we are only now discovering, I'll show you a couple of examples, only now discovering intergalactic stars that don't belong to any galaxy, but they're lost. It's very difficult. Very deep images are needed to find them, because you can see them in an aggregate in galaxies, but if there are stars moving around. So those are the baryonic component is gas and dust, which I haven't written here, but dust belongs inside the galaxy. There's gas in between the galaxies. There are stars in between the galaxies, and there are galaxies. These are the baryonic component. The non-baryonic component is the dark matter. Now, here's an interesting idea. So we know from the CMB measurements, and these are, of course, you've had lectures on cosmology. You know what the cosmic microwave background is. And we know that the cosmic microwave background, various fluctuations can be fit by models from which you can find some basic parameters. And one of the basic parameters that can be found from CMB is the omega in baryons, which means the fraction of the density of the universe, which is in baryons. Okay, so I don't know whether other people have explained this term little h, but this little h is nothing but the Hubble constant parameterized so that Hubble constant of 100 is 1, and Hubble constant of 50 is 0.5, and the small h is just Hubble constant divided by 100. Now, this kind of convention came because even 20, 30 years ago, we didn't know the Hubble constant to a very accurate number. It was somewhere between 50 and 100. But now the Hubble constant is between 68 and 72, right? We know there's still a debate We don't know where it is. So think of it as 0.7. So if that is 0.7, then this, well, 0.7, 0.67, say, or 0.72, whatever you believe in, 0.7, then the omega in baryons is roughly 5%, 4.9%. Yeah. And omega in matter, which is the omega, which means the density fraction of the universe in matter, is about 29%. So 29% of the mass energy of the universe, include dark energy and dark matter, and every form of matter, is 29%. And only 5% out of that is baryons. Okay, so remember that the rest of it then is non-baryonic, and that's the dark matter then. And other than this 28.9%, the rest of it, the 71%, is dark energy. So I'll concentrate on the baryonic bit first. So the baryon fraction of matter is 17%. So of all matter in the universe, 17% of it is baryons, which is the stuff that makes us up, quarks, protons and neutrons, things that are in the periodic table. Now, do we see that? So there are people who've gone out and taken a census, like you go and take a census of the population of a country. So there are people who've looked at all the stars that you see in all the galaxies. That's a very big task. But what you do is you draw what is known as a luminosity function, which means that you figure out the number distribution of galaxies in different ranges of luminosity. You don't have to count every single galaxy. You just, you count the galaxies, but you don't have to measure the luminosity of every single galaxy. You put them in little bins. You have a function, luminosity function, then you integrate over it and integrate from small luminosities to very large luminosities. And the total light is the curve, is the area of the curve. And thus you find the total evidence of light in the stars in the galaxy. And once you do that, you find the number that is 0.003. So these are all the stars in the galaxies. And I'm trying to find an omega that is 0.049, right? So you can see very small fraction of stars are in the form of the baryons are in the form of stars. If you take the neutral gas, which is the gas that that emits radio waves, it's atomic hydrogen, and it's this amount. If you take the molecular gas, the gas that's molecular clouds in galaxies, that will. Can you please switch off your? It's fine. I'm just muting people. I don't know what this is. Okay, and then, but then the interesting thing is that if you look at this whole thing, you can see that the gas that you find in between the galaxies in clusters. So I'm talking of the neutral gas in galaxies, talking of the molecular gas in galaxies. These are much smaller. Then if you look at the gas in between the galaxies in a cluster, which can be measured through their X-rays, and I'll show you how later on, that is comparable, and in fact might be even more than the amount of baryons in the stars themselves. So it's interesting that most of the baryons in the universe are in actually the hot form, 10 to the 7 degrees that emits X-rays. This number is actually a lower limit. It can be much more than that. But together, if you add all of these things, they don't add up to this number. But the cosmic microwave background, which essentially is a model of the Big Bang, tells us this number. So there's a big interesting question of where these missing baryons are, right? And some people say they're in a dark form, like short, small stars that you don't see because they don't glow. like white dwarfs or the form of black holes, things like that. And then some people say that we are actually missing out on a lot of the baryons that are not there. So that's a very interesting topic of research. We can see that actually there are a lot of stars in between the galaxies. I showed you this picture of the Sagittarius dwarf, which is one of the Milky Way's nearest dwarf galaxies. And you can see that it's being stretched as it falls into our galaxy. And what you see in this picture are the stars that are found that are stripped off this galaxy. And actually, the Sagittarius dwarf, the size of it on the sky is almost 270 degrees. It's going around our galaxy. As it goes around, it's being stretched because it's breaking up as it falls into our galaxy. So when you take a short picture, you only see this bit, but you can see that there are lots of stars that are outside the galaxy. So that gives you a clue. That there are a lot of stars that are not accounted for in when you look at the galaxies. Here's the best example of this. This is Chris Mihos's fantastic picture of the Virgo cluster. So in the middle of the Virgo cluster, so you have M87, which is here, which is of course the famous galaxy in the middle of the Virgo cluster, for which the first black hole image was formed about 15 megaparsecs away. And this is the middle of the nearest cluster of galaxies. And what you see in the middle are the few galaxies in the middle, but here it is the deepest image ever taken of any optical system. The way they did it was that their university bought one of the telescopes from the American Observatory. They were selling off small telescopes. So this is a 1 meter Schmidt. And they dedicated it for many years to study only one object. So every night, a picture was taken of the Virgo cluster using a digital camera. And this is the result of about 15 years of data. Every night, same object. And so it essentially beat down the noise, and you're looking at much, much lower than the sky background of light illumination. And as you see that, you see all these galaxies connect up. You can see star streams connecting every galaxy in the middle of the cluster. You don't see this normally. When you see a picture of a cluster, you see galaxies very isolated from each other. I wouldn't be surprised that if there are some streams of stars connecting the dwarf galaxies to our galaxy as well. So this gives you a clue that intergalactic star streams are very important, and nobody's yet quantified, apart from studies like this, how much of the baryons are in the star streams. I'll pause there and answer one question that came up in chat. In the chat, it says, how are these omegas measured? I explained to you that in the stars, what you do is you construct a luminosity function of all galaxies and integrate under it. So you take a catalog of galaxies that gives you a representative number of galaxies and their luminosities in a volume, and you extrapolate from that. You integrate over it. That's how you get the total number of omega, that is, which is total amount of density of matter or luminous matter in stars. You know the mass of the star, of our sun. You know how much light it produces. You find how much, what multiple of that comes from a certain galaxy. You can estimate how much mass there is in that galaxy. Similarly, you do the same thing for neutral gas. You do radio surveys, galaxies that are measured in radio, the 21 centimeter line, that tells you how much atomic hydrogen there is in galaxies. You do a luminosity function and you integrate. You do the same thing for molecular gas. You take the CO molecule or the OH radical, and you use a millimeter wave observatory like ALMA, for example, and you measure the luminosities of of a certain molecule or related molecules, then you try to find how much there will be. You know that if there's so much H2, there will be so much CO and so much of the other molecules. And from these models, you can figure out how much molecular gas there is. You do the same thing for X-ray emission from clusters to show how much of the very hot baryons there are. And from an all-sky survey, you add up and make. So this is how these things are calculated. And people who are giving lectures on the CMB will tell you theoretically from the other end how the omega components are calculated. So here's an example of how you do a radio survey. Radio, this is, I showed this picture before also, a picture of the galaxy, which is seen in stars, the optical part of the galaxy, spiral galaxy. You can see a negative here. That's a negative grayscale picture. On top are contours from a radio telescope. And the radio telescope is measuring the radio emission at a wavelength of 21 centimeters, 1420 gigahertz frequency. And that's, as you know, is the transition. Is a transition, a spin flip transition of hydrogen, where the nucleus and the electron, there's only one electron in hydrogen, are parallel to in the antiparallel. That transition is a forbidden transition, but not forbidden for astronomical objects. And so that is actually the most common transition in all of astronomy, because hydrogen in this form, in the atomic form, is everywhere. And the atomic hydrogen emits this. And so you can see that, and this is what Vera Rubin, for example, used this kind of observation to find things very far away from the center of the galaxy to find rotation curves. So you can actually also measure from how much neutral hydrogen you see in galaxies. You can add them up and find out how much there is in how much of it there is in the galaxy. You can do that in all galaxies in a cluster, add them up, and that you get the omega in baryons in hot gas. I showed you this picture before also, M81, M82, that's M82, that's M81, that's another galaxy. And as I was telling you, if you see just a picture of an optical picture, it doesn't tell you the whole story, because on the left is the picture taken in radio at 21 centimeter, the cold gas. And you can see the galaxies are exchanging cold gas. If you took a very deep picture of the right-hand optical image as well, like Chris Mihos did for the Virgo cluster, you would probably see star streams as well being exchanged between them. But it's very difficult to do, and it's been only done for that system. So I'm sure other people will do this system next, because this is a very close nearby group of galaxies. And you will see that as you see the cold gas being exchanged, the atomic hydrogen being exchanged between the galaxies, you will see the stars also being exchanged. You look at I'm showing you 1689 again, just to contrast between systems like this and systems like this. So imagine now, you have hundreds of galaxies in a cluster. How much interaction is happening between them? This is a nice Hubble Space Telescope picture. Even though Hubble Space Telescope is our best instrument out in space, it's only a 2-meter telescope. When we get into, in 10 years' time, 30, 40-meter telescopes, and we get the first images that will come from the JWST, which is much, much bigger than the Hubble Space Telescope, and they'll start coming from the middle of July, you will see how much more there is between these galaxies and these clusters. And we're waiting to find out about such things, because they will tell us where where the baryons are. I mean, even the puzzle of dark matter and dark energy is there, but just the baryons, just the kind of elements we are familiar with, we don't know where they are. And so we talked about the cold gas. which emits radio. The hot gas, as I said, emits X-rays. And this you find not in galaxies, in our galaxy that is. You find actually hot gas around very large galaxies, but you find them in between galaxies in clusters like this. This is a purely optical picture from the HST. Here, everything in this picture is a few thousand degrees hot, and that's why they emit. If you think of stars as black bodies, their peak is when there are a few thousand degrees hot. Their peak are in the optical range. Our sun, for example, the peak is 550 nanometers. Here, so all of these are emitting light, real light, optical light. In this particular case, however, here on the left is the same cluster, Abel 1689. But now on top of that is superimposed the Chandra X-ray image in purple. Now look here again. Look at this part. You can see those are stars in the foreground, but these yellow things are all elliptical galaxies in the middle of the cluster, right? And if you stare at this, you will recognize this, right? That's the spiral galaxy. These are the elliptical galaxies. Those are the stars in the foreground. And on top, you can see has been superposed the X-rays. And you can see how the X-rays fill the entire core of this cluster. You can see X-rays all over this place, right? And this kind of X-rays that are detected by the Chandra X-ray satellite is emitted by 10 to the power 7 degrees hot gas, right? And I'll talk about that, where that gas comes from in a moment and what it tells us, but it certainly tells us that this gas is being heated up to these temperatures. How? It's simply because the fact that the matter that constitutes the cluster, that holds it together, dark matter, forms a very deep potential well. And in this deep potential well, the gas is just sloshing around, and the thermal energy of the gravitational potential makes it hot enough to emit X-rays. So if you look at the balance between the potential energy and the kinetic energy of the particles in this system, the thermal energy, if you just write it as kT, you will get the T as such a high temperature. And just so shows how much massive these clusters are, that to be gas in a cluster like this, it has just moving around, you can be heated up to these temperatures. On the right is a picture which shows only the X-rays. Now the galaxies have been taken out in another cluster, Abel 2125. And you can see how smooth the distribution of gas is. Of course, all these are galaxies that if I had shown you the superposed picture, you would have seen. But sometimes when you see a picture like that, you can see much more structure. Here, I don't know whether I can show you. No, okay, fine. So here is so I've showed you neutral gas. I've showed you, I haven't showed you pixel-molecular gas that's very similar to nuclear gas. I've shown you stars in between the galaxies, and I've shown you hot intergalactic gas. And then there's dark matter. If you remember, I showed you how Peter Rubin found dark matter on the outskirts of galaxies. And these are galaxies that have dark matter halos on its outskirts, right? I've shown this before to you. But this dark matter is also there in between the galaxies of a cluster and all around the cluster. And I'll show you evidence of that in a minute, not just in these galaxies. But now, I'll also mention in passing here, if nobody else has done, that people have for a long time been extremely unhappy with dark matter, because we have not detected this dark matter yet, other than from gravitation. So a lot of people have tried to find other origins of dark matter, or the kind of effect that we see of dark matter, right? And one of them has been this thing called MOND. I don't know whether anybody else has talked about it in this full course. This has been there from the 1980s, right when I was a student, and proposed by nobody less than Mordecai Milgrom, who, of course, with Hawking, did all those famous black hole thermodynamics theorems. And Milgrom's idea was that what if Newtonian dynamics doesn't work on the scale of galaxies? If you take galaxies and clusters on a very large scale, the Newtonian gravity equation that we use, F equals gmr square over r squared, has an extra term that only works on very large scales, but becomes one on very small scales. Now, this modified Newtonian dynamics was tried to find was tried to, so it just gives you an extra parameter to play with, because it would be an exponential term with a certain scale, and that scale would be quite significant on galaxy and cluster scales. And it turned out that you could fit some of these rotation curves with such a law without needing any extra matter. The problem is that it ran into problems because though it fit rotation curves and similar things, then the same law doesn't apply for cluster scales. It doesn't work, and it would not fit other things that would produce dark matter, like as I will show you how the presence of dark matter is measured through gravitational lensing and also through X-rays. Okay, so alternative theories of dark matter are a very interesting way of exploring things. A lot of PhDs have been done on it. A lot of research, even in India, a lot of research has been done on alternative theories to dark matter, which will produce the same effect, but one needs a theory that can produce all the different effects of dark matter that we get. I have a question in the chat box from somebody who asks, what is the size of these clusters, etc. So a typical size of the cluster would be 1 or 2 megaparsecs. You remember in our local group, the nearest galaxy is about 0.7 megaparsecs away. The size of our local group is about half a megaparsec, or a fraction of a megaparsec. So if you look at something like this, a cluster like this, from the center out there would be 2.5 megaparsecs, something like this. Okay, so a small group would be around this size, a few galaxies, and so here you will have a few hundred very large galaxies packed into a volume whose radius is 2.5 megaparsecs. So that's the size of clusters. So what I said was, so alternative theories of dark matter don't really help. So we have to find some way of finding this dark matter, and particle physicists are working very hard on trying to find detect these dark matter particles. They have to be particles that are not baryonic directly. In galaxy clusters, we find this matter. So I've talked about baryonic matter. Let's talk about ways of finding the matter, the real component of matter, which is the predominant component, the dark matter in clusters. In galaxies, I've shown that you can find them through rotation curves of spiral galaxies. In clusters, on cluster scale, the largest scales in which dark matter exist, we can find them by the dynamics of the clusters, by velocity dispersion. We can find them by the hot gas in the clusters, in the X-rays, and we can find them by gravitational lensing. And in the rest of today's lecture and in tomorrow's lectures, I'm going to talk about these three methods of finding galaxies. So let's talk about the dynamics first. So this man called Fitzwicki, in the 1930s, as early as that, took the Coma cluster, which is one of the nearest galaxy clusters, just beyond the Virgo clusters. This is about 100 megaparsecs away. The Virgo cluster is 15-20 megaparsecs away, something like that. The nearest rich, and it's not a very rich cluster, the nearest rich cluster, about 100 megaparsecs away from us, is the Coma cluster. And Zwicky, with a funny picture here was one of the greatest astronomers of the early part of the 20th century. Worked in Caltech, and he after Hubble first started measuring the redshift of galaxies, he started looking at some of these clusters of galaxies, and he chose a Coma cluster, and he measured the redshift of many galaxies in the Coma cluster, and found their relative velocities. Of course, remember that when you're finding redshifts, you're finding only one component of the redshift, of the velocity, that is the radial component. You know nothing about the transverse components because they don't contribute to the redshift of the cluster. But if you have many galaxies, then you can statistically, just like you do in kinetic theory of gases, you can statistically estimate the three components from one component. Right? So Zwicky made a very bold statement. Remember, this is 1933, 3 decades before Vera Rubin would talk about dark matter in spiral galaxies. She did her work in the late 60s. 1933, he measured all these, and he used a simple argument from the virial theorem, which I'm going to now show you, to show that the mass that you get out of the Virgo cluster is much more than the mass that seems to be there in the galaxies themselves. So here's the Coma cluster. There are 2 central big elliptical galaxies with some smaller galaxies, and there are a few hundred galaxies in the whole cluster. It's a very rich cluster, and with a radius of about a couple of megaparsecs or so. Zwicky used the virial theorem, and I'm sure other people in this course have used the virial theorem before. And a lot of you would have encountered the virial theorem. If you are a teacher of physics in classical mechanics, I'm sure you teach the virial theorem. It's in an appendix in Goldstein's book, derived in full glory. If you are an undergraduate who's coming to astrophysics for the first time, you might not have encountered the virial theorem right now, but other people might have used it. It's a theorem that's used quite a lot in astronomy. And it says that if you have a system of gravitating particles, where everything is, and you have a system of n particles, all of whom are pulling each other with an inverse square law force like gravity, then if you take the second derivative of the moment of inertia with respect to time, then half of that is equal to this quantity on the right. And the quantity on the right is T. T is the time averaged total kinetic energy, like that. And the V is the time averaged total potential energy. Okay. This is pretty simple to understand. You have lots of galaxies or point objects or whatever, stars. This applies to particles that make up a planet. It applies, protoplanet, that is before it becomes a solid planet. Or you have, stars in a cluster or galaxies in a cluster. In this case, he's applying it to the Coma cluster. Talking of these, imagine each of these galaxies being a point object. And if you take the total kinetic energy of all of these galaxies, and you take the total potential energy of all of these galaxies and you can measure them, then together they will give you this quantity, which is some derivative of the moment of inertia. Now, in this particular case, the moment of inertia of a system changes if the whole system is either collapsing or expanding. If it is in equilibrium, and so Zwicky assumed that, say, a cluster of galaxies is in equilibrium, which means that it is already been formed, it's not collapsing anymore, then the left-hand side is 0. right? Its moment of inertia is not changing because the moment of inertia is this quantity, which is proportional to mr squared. It has dimensions of mr squared, and those are dimensions of the cluster. And if it's not expanding or contracting, then it just means that that is zero. So the virial theorem is used for systems in equilibrium. It does not apply to things that are in a process of violent interaction or merging or things like that. But if you take a system of particles that are just gravitating and in equilibrium, then 2t plus v equals to 0. Now that is a very easy way of finding quantities like that. Okay? I have a question in there, and which I will answer. Don't worry. Then you know, if you're a teacher, then you teach this all the time. If you are a student of physics, then you know how the gravitational potential energy of a shell of a sphere is calculated. You break it up into shells, and then you bring each shell from infinity to this its place in the sphere, and you figure out how much work needs to be done to bring a shell from infinity to you to the sphere, and that amount of work adds up into the gravitational potential energy. In fact, since gravitational is attractive, the amount of work you do is negative. So gravitational potential energy is negative. So each of these shells would be 4 pi r squared, 4 pi r squared dr times rho of r. And imagine for the time being, this is not true, but of course, the next order of magnitude would be to make it more complicated. This can be done. This is done in all astrophysics books, but just for the sake of this lecture, I'm talking about rho being constant. So imagine this rho being constant, then 4 pi r squared dr, or you can make it rho equal to some mean rho bar. Yeah, you write the total gravitational potential energy as an integral of the amount of work that is done for each of these shells to be put together. And this can be done, this is worked in all books. And the result you get is minus 3/5 gm squared over r. Do the same thing for a sphere of charge and stuff like that, something that, this is a very favorite problem given to first year physics students. So, the total potential energy of this particular sphere. And so what you've done is you imagine the cluster, like the Coma cluster that we saw in that picture, to be a sphere, or maybe the 1689 that we saw. I don't know where it's gone. It used to be there. Yeah, it's a sphere. They look spherical. And you assume that it's in equilibrium, even though there might be some interactions going on, etc. And but as a first approximation, you imagine it to be a uniform sphere, and you get minus 3/5 gm squared over r. That's your u. That's your total. It's exactly the same as what I call v here, right? This v in this particular virial theorem is that minus 3/5 gm squared over r. How do you get the t? The t is if you take all the galaxies that belong to the cluster. And there's a question in the chat box asking, how do you know the galaxy belongs to the cluster? Good question. If you find all the galaxies that belong to the cluster, and what you do is you find its velocity dispersion, which means, say, for example, if you take the galaxy, now the whole cluster as a whole is going to be moving away from us because of this expansion of the universe, right? So the cluster itself has a mean redshift because it is in the flow of galaxies in the universe. And what you're really interested in are the speeds of the galaxies inside the cluster moving in random directions, right? To find the random motion, which will contribute to this kinetic energy term, the t term, what you do is you subtract the t you subtract the subtract the v of the mean v of the cluster from the radial velocity of each galaxy. You take the difference and you calculate this quantity. Okay, and what does this quantity look like? It looks like the dispersion that you get in statistics, which is the square of the standard deviation, right? So that's why it's called the velocity dispersion. So here is an example of the Coma cluster. Here you can see that each point here we are somewhere here, and you're looking out. You can see that these are galaxies that are plotted on the sky, and this is on the left is a histogram, and you can see that in that direction you've measured velocities, and Zwicky did this for, I don't know, 10, 15 galaxies. Now if you go to the Coma cluster in some catalog like the Sloan survey, and you take all galaxies within 2 megaparsecs or something of the central galaxy and extract all of them, you'll get about 1,000 redshifts. And you plot them, and you will see that there are some that are very low. They are probably in the foreground. There are many in the background, but there will be a peak like that. And this is the answer to the question somebody asked in the chat box. How do you know a galaxy belongs to the cluster? In order to belong to the cluster, it has to be within a few hundred kilometers a second of the mean velocity of the cluster, because you can see from this histogram, you can choose to cut off here and cut off there, and you will get a Gaussian peak, or almost like a peak. And then that will be the cluster, all galaxies that are within that peak. And there are many hundreds of galaxies in there. See, this 100 here. And it's the dispersion, the velocity dispersion, that gives you this number. Okay? And once you take the velocity dispersion, the radial velocity dispersion, you have to multiply it by 3, just like you do in kinetic theory of gases. Because it's one component, statistically, you have 3 components of velocities. So you multiply that by 3, and then you get 3/2 m sigma squared. I hope you understand how it's done. So for V, you get minus 3/5 gm squared over r, for r being the radius of the cluster. And here you get just 3/2 and sigma squared, which you can measure from this this particular diagram. And once you do that, then you bring that all together. 2t plus v for the spherical cluster is minus 3/5 gm squared over r. For t is 1/2 m sigma squared, and you multiply that by 3, because sigma r squared is measured from that histogram. So m of r, the cluster, the total mass, and this is the mass that is the dynamical mass. It has nothing to do with the galaxies you see. It is the mass that causes the random motion of galaxies in there. Its total mass includes dark matter, and is actually dominated by dark matter. Is this quantity 5 sigma r squared r divided by g. Okay. So now if you take r of 2 megaparsecs, I just said that's a rough radius of the cluster, 2 megaparsecs, and you take the measured sigma r, the velocity, the standard deviation of radial velocities in the Coma cluster, it turns out to be 1200 kilometers per second. You plug that in, and you get a number that is 3.5 times 10 to the 15 times the mass of the sun. If you compare that with the total mass of the galaxies that you see by scaling with the mass of the sun, then that's about 100 times more. Right? And this is what vindicates Zwicky's theory now, and shows that just that from the dynamics, you made many assumptions. You made the virial theorem is valid because it's in equilibrium, it's spherical, all those things. The potential energy term came from assuming it's kind of density is equal, etc. All those things can be modeled, and I did a very strawman calculation here. You can put a much more realistic density distribution of a cluster. You can do all kinds of corrections for various things that we've calculated, but still you'll come up with an answer that's not very far from this. And that is the fact that the amount of matter that holds a cluster together is about 100 times the amount of matter that we see in the galaxy. This is what Zwicky said. And so the idea is that most of the matter in a cluster is dark. And if you look at the galaxy scales and estimate the amount of dark matter that holds a galaxy together around a galaxy, that comes to be about 3 or 4 times the mass of the galaxy in stars. For a cluster, it is much more. It's many hundreds. And so there is much more matter on cluster scales than there are on galaxy scales. So I'll stop there today. I'll come back to this topic when I come back to tomorrow and talk about other methods of measuring galaxy, the mass of galaxy clusters. Very quickly, if there are a couple of questions, you can unmute yourself. You can put up your hand and ask questions. Are there any questions? Yes, Akshat, go ahead.
Hello, sir. Can you hear me?
Yes, I can hear you.
Sir, when galaxy clusters themselves are merging, then how are we able to map dark matter? Because that is not an equilibrium condition.
Yeah, so I'll talk about that tomorrow. That's the best way to do that is through gravitational lens.
Oh,
because that's a direct way of doing it. It's not through dynamics. Because when you use dynamics, you're using assumptions of equilibrium, and those are not equilibrium systems. Okay, you can measure, you can find the matter distribution through both X-rays, which I'll talk about tomorrow. I'll talk about X-rays and gravitational lensing. X-rays give you also a way of tracing that dark matter. It is hard to measure because when you measure mass through the X-ray emitting gas, then you have to make certain assumptions about equilibrium. But gravitational lensing is actually straightforward. There is no assumption of equilibrium. It is a geometric method of measuring mass. Have you had lectures on gravitational lensing yet?
Not yet, sir.
That's going to come later on. So I'm going to give you an introduction to it, and you'll do it in much more detail later on. Okay? Okay, next, Ajay. Ajay is next.
Hello, sir. Am I audible?
Yes.
Yes, sir. I wanted to know that there is another term known as globular superclusters. What are those things?
No.
Like, are they same as clusters or?
No, there are no globular superclusters. There are globular clusters, and those are star clusters that are within the galaxy. There are superclusters, which are clusters of clusters, and I'm going to talk about that tomorrow. Those are the largest structures in the universe. Right? The superclusters of galaxies are the largest structures. They're made up of many clusters of galaxies. And I'll talk about that tomorrow.
Okay,
there are no globular superclusters.
Okay, sir. Thank you so much.
Anybody else? Looking at the chat box. Pratik has asked in the chat box, can we say anything about the distribution of dark matter around these clusters? Yes, of course. They're not distributed uniformly. And absolutely, the distribution of dark matter can be measured. There are models that are fit to the distribution of dark matter. And I won't have time to go into great details about these distribution functions, but those are things that you can learn later on. But I'll show you how that is done from both, from all of these. You can, for example, take the distribution of the random motions of galaxies, and you can break them up into shells, and you will find that the galaxies in the middle of the cluster are moving much more randomly than towards the end of the. So you can have a velocity dispersion, that sigma, as a function of r, right? And that has been done. I myself have done it for the Coma cluster and many other clusters. If you have lots of galaxies, you can do that. And if you have sigma as a function of r, then from this dynamical method, you can try and fit a model, which is rho of r of dark matter, to these random motions. And what one finds is it's mostly rho going off as a certain model, which is called the sphere, and things like that. So they are distributed in different forms. If you are curious, you can look up NFW models, for example, Navarro, Frank, and White models, which are the most common forms of dark matter distribution in clusters. Yeah, you look them up on the web and you find. I won't go in. I won't have time to go into that kind of detail. Last question. Tanishk has a question here which says the gravitational field. Does the gravitational field have stronger effect within the cluster of galaxies than the field within each of the constituent galaxies? Absolutely right. Because the galaxies themselves have dark matter halos that are small, that are holding the galaxy together, but the total amount of dark matter in the cluster is absolutely huge, and that's holding the whole cluster together. And the strong field on the large scale, the effect of that within the galaxy is small. So inside the galaxy, I'm feeling the gravitational field of the dark matter that is holding the galaxy together on the smallest scales. Remember, gravitational attraction goes as 1 over r squared. So on kiloparsec scales, the gravitational field of the dark matter is very important. On megaparsec scales, gravitational field of the cluster is important. Srikanth, last question.
Yes, I was just wondering that if you ever have a strong evidence of dark matter, would it come from the particle physics or?
Yeah, so a lot of people are trying to do this. This is a major activity of particle physicists to try and find dark matter particles. The problem is dark matters are non-baryonic, and so they don't interact with baryons. They don't have charge. So it is hard to build an instrument with which these things will interact in any other way than gravitation. So you can look up. I won't talk about the experiments that are being performed to find dark matter. There are experiments being performed to find dark matter in interactions in CERN, for example, when the beams are collide, whether they produce dark matter particles. These things don't interact at all. They go right through all our instruments. There are large experiments that are because there are models of these dark matter particles. So for each kind of proposed dark matter particles like axions or massive neutrinos or things like that, people have designed experiments to find them, but nothing has been found yet. So from the particle physics angle, it's absolutely important that we find them. Otherwise, only through gravitation we are feeling their presence. And so there are a lot of people who are skeptical that do these things still exist? Do these things, how do they come? I mean, where do they come from? What is the origin of this dark matter? This is not well known at all. So that's something that one can understand if one can start finding out what these particles are. Right now, there are many, many different candidates for these particles. So okay, I hang up for now, and I'll come back tomorrow at the same time. Okay, thank you.
Thank you very much.